Okay, so we have talked a little bit about how a lot of the concepts we use in math, in fact, a lot of the entire branches of math that we use today come from our observations of the natural world and our attempt to explain them. And when we see the word trigonometry, the first thing that might come to your mind is triangles and angles, triangles and angles. But there's actually more to it, and kind of the foundations behind trigonometry are not they're not actually triangles, but they're circles. So what are some things we know about circles? And I invite you to pause the video here and you can kind of make your own little list of things you know about circles. But here's my own list of just some things, and these might be some of the things you wrote down or thought of. But we know that the area of a circle is pi r squared. We might not know why the area of a circle is pi r squared. The circumference of a circle is 2 pi r, which is the same thing as pi times the diameter. Okay, we also know pi, right? Pi is something that has a lot to do with circles. If you've worked with circles before, you might know that the equation of a circle centered at the origin on a coordinate plane is x squared plus y squared equals r squared. And we might also know if you've dealt with conic sections at all that this next equation here is kind of a version of this one where the circle is not centered at the origin, but it's centered at some point on the coordinate plane, the coordinates of that point being hk. And I think something we all know about circles is that there are 360 degrees inside of a circle. Like this here is a very important thing, and I think we take for granted a lot. Like, what is the significance of that? Why are there 360 degrees? So why are there 360 degrees? There might not be a totally clear answer for this, but let me do my best to explain. So right now, if you look at your hand, if you put your hand out, palm towards you, and you see that you have four fingers and your thumb, and on your four fingers, like if you look at each finger, you have like three, and this is assuming you have what is considered a normal hand. Uh, that you have three kind of like joints on your hand, or you have three. You can think of it as little joints on your fingers, or you can think of it as the bones in your fingers. And you can count. Each of your fingers has three of these like creases, these little joints, or three bones. Okay, and you have four fingers, and so if you counted all of those joints, you'd have a total of 12 on a hand. And we have five fingers total, including the thumb, and so 5 times 12 is 60. And so all these numbers I've mentioned, 5, 12, 3, and 4, all of them are factors of 60. And this is significant because the same civilization, the Sumerians, and then the Sumerian civilization passed all this stuff on to the Babylonian civilization. They used a number system called base 60. Now we use like modern times, we use a base 10 number system, and it's actually we think that that's for a very similar reason. If you just count your total number of fingers, you've got 10. And so that's really easy for us to think of conceptually, like what 10 is, and like 10 tens and like 10 hundreds, etc. Uh, but the Sumerians thought similarly about 60. 60 can be divided in all these different ways, and so they used what was called a sexagesimal number system, or a base 60 number system. And so these them being the first people that were like considering these kinds of things, like it was natural for them to use a number that works well in base 60. But why 360 specifically? Well, let's take a look at this. So these two things here, right? This thing in the top picture is called an analemma, and what an analemma is it's basically a map of the path of the sun in the sky. So this picture was taken basically taken one picture per like month or per set number of days at the same time of the day at each day, and it's like a composite picture of all the locations of the sun in the sky. And you'll notice it does this strange path where let me try to draw on this. So this here could correspond to like the middle of the summer, and then up here is like the winter, and then it comes back to summer, and then this is like This is like the fall or something. This is the fall down here, or this is midsummer maybe, I guess. And then it comes back here, and it does this like figure 8 pattern, and that's like it will repeat year over year. It makes this like infinity sign. This is this scene, this shape might be most famous for its use in the movie Castaway, where Tom Hanks he used a pinhole light in his cave, and he seemed to have plotted out every day how the sun, like where the sun spot was. This is actually impossible for that movie because Tom Hanks didn't know what time it was every day. This would only work if you took a picture, if you recorded where that light was at the same exact time of the day every day. And he's on an island with no like watches or anything, so you didn't know what time it was. But anyway, this shape here, it turns out that if you do this, if every single day, that there are it's a 365, like we know that this would rematch up, these would touch each other again, that this line would connect. Like if we had this line and we drew it, it would be 365 days until it got back to where it started, or where we started drawing it. And 365 and 360 are not very far off. And if you weren't super precise with your measurements of the day, it could be thought you could reasonably expect that the margin of error is just 5 difference between 360 and 365. So they're like, oh, it's 360. That's pretty convenient, because then they can go on and divide that 360 and into parts. Like there are 6 60s, right? There are 4 90s. There's all these kinds of nice divisions of 360. And we can, in a circle, like get pretty precise with just a degree, but if we needed to be even more precise with an angle, we could just divide an angle by 60, and that's known as 1 minute. And if we divided an angle, a minute by 60, that'd be known as 1 second. So if we think about 1 second is 1/3600th of 1 degree, which is an extremely precise angle measure, and it's actually used in a an angle measure system called degrees of minute seconds. And degrees of minute seconds are not used that often anymore, but they are still used a lot in like navigation. So if you're like want to know if you set off, on a long distance across the ocean, and you set off at an angle that's even a few seconds off, you could potentially, because we could be going such a far distance, you could potentially be going way off course. And so for navigation and for certain applications, very precise angle measurements are necessary. So to apply this idea of an angle, it's also important to come up with some standards for how we go about measuring them. Like we need to have reference points. And in trigonometry, when we refer to angles, we're very commonly talking about angles in their standard position. And in their standard position, what that means is if you're like starting with the origin and you draw a ray, so you draw a ray out from the origin in a positive x-axis direction, we call that the initial side of an angle. And then if we were rotate counterclockwise, and we end up with another ray, we draw another ray from the center of the circle out, the angle, that's a positive angle measure. If we're rotating counterclockwise, that's a positive angle measure, and theta is kind of the Greek letter we use to represent an angle most often. And so that would be a positive angle. And so this angle here, this might be positive 45 degrees. Okay, you don't write the positive if it's positive, but it's about positive 45 degrees-ish. Okay, but we can also have negative angles, and negative angles occur when we are doing kind of a negative rotation. Okay, sorry, a clockwise rotation. So clockwise is negative. So we're going from our terminal side rotating clockwise. We have the negative angle, and that'd be the same. We're saying is that angle and that angle are the same angle. And so this might be like a negative 45-degree angle. So the standard position of an angle, knowing that we're always measuring angles off the horizontal axis, in fact the positive horizontal axis, is like the positive x-axis. That's very important. It keeps things consistent throughout our calculations when we're talking about trigonometry. So we just said that counterclockwise rotation is positive, like we have positive angles when we go counterclockwise from the terminal side, from the initial side to the terminal side, and clockwise is negative if we go from the initial side to the terminal side, and that's if we're going clockwise that direction, that's a negative angle. That's confusing to me. Why would that be? Well, let's talk about why clockwise is clockwise. So civilizations that started to tell time, and just tends to be the case that most people in the world, on Earth, live in the northern hemisphere, and so. If you live in the northern hemisphere right now, and statistically speaking, you probably are. If you went outside and it's during the daytime and you face north, uh, the sun, if you sat outside the entire day, the sun would rise on your right and set on your left. It rise in the east and set in the west. And as the sun is in the sky, it's behind you, so the sun is at your back, and that means that so you're standing. So imagine this is you. You're standing right here. The sun rises over here, and it's going this way, and it's going to set over here. And as that's happening, you can imagine that there would be a shadow. Your shadow, as you see it, would be over here in the morning, and then it would go this way and be over here in the evening when the sun is setting, or in the afternoon. And so this is why we get clockwise. That this is a sundial, by the way. So the direction of your shadow, or the way you would tell time based on these tick marks along the sundial, is going from left to right. And so as you see it, and that's why clockwise is clockwise. If you're in the southern hemisphere, just face south, and you'd have the same situation. Okay, now why then is it that why don't we have positive? Like, why is clockwise not positive? Like, counter is, we consider that like a negative word. So, like, why would that be? Why is that the way it is? Well, I don't really have a great answer for that, but I can tell you that there's such thing as the right hand rule. And the right hand rule is used in physics a lot. It's used in math too. And if you think of a coordinate plane, convention says that that's the positive x direction and that's the positive y direction. And we like working with positive numbers a lot, so we tend to be in this quadrant of the coordinate plane very often. If you take your right hand and you put it in front of you, and you curl your fingers in, you'll notice that you're giving a thumbs up sign. So you stick your right hand out, you curl your fingers in towards your palm, you're giving a thumbs up. That's positive. If you instead, right, if you curled so that's like, as imagine you start with your hand on the positive x-axis and you curl them towards the y-axis. So now if you did the same thing, kept your right hand out, and now put your fingers along the x-axis and curled them towards the negative y-axis, you'd be kind of pointing down. You'd be pointing down or away from you, and that would be like a negative thing. This seems dumb, but it is the convention we use for stuff in physics like magnetic fields and torque, and in math when we do cross products, we start getting into three-dimensional space, and we see all kinds of applications for this. And so maybe that's not the best possible answer to this question, but hopefully it gives you some clarity in the reasons why this is the way it is. So since we can have positive and negative angles, it's possible to describe the same angle in two different ways. And what that is basically is called a coterminal angle. And so in this example here, we can describe this angle, like this angle right here, this position, you can think of it as a position, can be described as a positive angle of 210 degrees or a negative angle of negative 150 degrees. And two angles in standard position are coterminal angles if they have the same terminal side. Let's look at some examples of angles that would be coterminal. But let's also familiarize ourselves with drawing angles in a standard position first. So we want to draw these angles in their standard position. So a positive 135 degrees. Well, I know, so this total circle is 360 degrees. So if this starts at 0 degrees here, that's our initial side. Then that means 90 degrees would be here, 180 degrees would be over here, and then if we add another 90, that'd be 270 degrees. We've divided that 360 degrees into 4 equal segments. Okay, so now if we draw this angle 135 degrees, we'd go the 90, okay, and then we'd go another half of that, so for another 45 degrees. So this right here, this would be our 135 degrees. Positive. Okay, 190 degrees, so we'd go our 90, and then we go another 90, that's 180, and then a little bit more, 10-ish. Okay, so that right there, maybe something like that. That would be our 190 degree. okay, the green one. And then the red one, negative 45. So now we're going to go counterclockwise, and we only go half of our 90. And so that would be like a negative 45-degree angle. That's how we would draw those angles in standard position. Now let's talk about coterminal angles. Okay, so what angles would be coterminal to these angles shown here? Well, so for the blue one, a coterminal angle would be this one. If we draw in that angle right there, we want to know what is that angle. Well, okay, so 135, we could say it's 360 minus 135, which would be 225 degrees, except it would be negative. Okay, so this angle we drew here, this is negative 225 degrees. So negative 225 for that one. Similarly, we can say for the 190, if we took 360 and we subtracted 190, that would be, what would that be? 170 degrees. So that means that this angle right here, okay, that angle right there, that's negative 170 degrees. So negative 170. And then for the 45-degree angle, the coterminal angle would be this one. We'd go in a positive direction until we got to that 45 degree. So we'd have, we can do this again, 360 minus 45. Okay, that is 225 degrees. Okay, sorry, no, it's not. It's 315 degrees. Okay, and we'd say it's positive now. Okay, so positive 315 degrees is this red angle that we drew. So those would be coterminal angles to the angles shown. And I want you to start thinking about angles as like locations on a coordinate plane with respect to like a circle. And if we can start thinking about angles in that way, a lot of what we're going to talk about coming up with trigonometry is going to kind of come more, I think, more naturally.